Another draft physics video presentation. Looks like it's recording adequately. So, Sabine Hossenfelder, Sabina. Anyway, the subject is atoms, but it doesn't really matter what the subject is. Her catchphrase is physics without the gobbledygook. But it's all gobbledygook in the sense that there really isn't any explanation for any mechanisms. There's just no mechanisms. There's just, space is bent, or photons cause magnetism, or some kind of virtual photon. And then when it gets to atoms, they have things as strong nuclear force. It's just some magical force that comes out of nowhere that somehow enables protons to get closer to each other, but no real mechanism. And so they just tell you a story, a story of their Big Bang, and this is what happened, and they have a story, but it's a story not made out of where they can point you to a trail of evidence, where they have the knife and it has the professor's fingerprints on it, and there's a note and there's a handprint on the window. They can't show you a chain of evidence because it's all just a surmise, made out of a loose impression where they can't fit it exactly, so they don't fit it exactly. They just give you some vague notion, because if they try to make it exactly fit, it'll be kind of obvious that the puzzle piece doesn't fit. That, the guy you're accusing of the crime was actually, in Bermuda or something at the time. Something like that. I'm just going to critique this classical kind of description, what is now their classic physics, the established story they tell. And I'm just going to point out that they don't really know how it really functions. And not even close, but they're going to tell you the story anyway. And there should be a German word for that, like Schnuckenflirter or something, for when you're jumping the evidence, when you're drawing conclusions way before it's cooked. It's just an underbaked theory, and they just should fess up that what they're talking is just talk, and there could be lots of different stories told, but because they all believe in the same kind of elves and leprechauns, they've created a whole forest full of places for leprechauns to go to sleep, and it has all a bunch of features in it, that I would argue if they started with a different story, they wouldn't need those stupid features, and they could get rid of those impediments to getting to the truth. Something like that.
Matter.
Bring this one back. Anyway. Just inconveniences of video making, I suppose. Right off to that. So continuing. Probably.
Atoms. You all know that. But where do atoms come from? When were they made? And how? And what's the island of stability?
So whatever this is. Right, so that's not gobbledygook. The island of stability isn't gobbledygook. Yeah, it sounds like gobbledygook island. How are they made? Well, why don't you say, what were they made of? And how did the stuff they're made of get there to be made out of that? There's lots of, circular reasoning.
That's what we will talk about today.
I did want to speed this up.
At first sight, making an atom doesn't seem all that difficult.
All right, so you could say that, but, prove it. Okay. Wow, that's not what I wanted to do. Move this over, move this up, move this there, get the speed. All right, well, it won't go twice as fast, but she does have an accent and whatnot. Okay, that should do. Sorry. My bad. Should have had this done before.
All you need are some neutrons and protons for the nucleus, then you put electrons around them until the whole thing is electrically neutral.
Right, and where do you get all that stuff from in the first place, right? But anyway. So let's continue. So, that part, is agreeable.
Done.
But having these electrons orbiting around, totally unnecessary. You can just, charge will take care of it all of it's on its own. You really don't need them to be hurling around. So once they figured out that atoms are made out of these positive and negatives, you could just make a sort of a magnetic model of an atom where they're in stationary positions. And it makes so much more sense.
Sounds easy, but it isn't. The electrons are the simple part. Once you have a positively charged nucleus, it attracts electrons and they automatically form shells around the nucleus.
All right, so it attracts, by what magic? So again, they don't have anything real in this description, so you can't really make anything out of it. Just magically attracts. What does that mean?
For more about atomic electron shells, check my earlier video. But
no, I don't think I will.
Making an atomic nucleus is not easy. The problem is that the protons are all positively charged and they repel each other.
Yeah, just as much as the electrons repel each other. Frankly, and that's sort of a giveaway. They have the same charge. So that's interesting. And so in a way, it tells you something about the fact that they do end up balancing each other, theoretically.
Now, if you get them really, really close to each other, then the strong nuclear force will kick in and keep them together.
And will keep them together. See, this is just a magical force kicks in that overcomes the strong repulsion. So you have this kind of the magnetic thing, where there's a strong repulsion. I mean, I just cannot cram these little magnets together. They just won't do it. They just won't. And you can feel it. You can feel they're not willing to do it. It's the same kind of force. And so you have to come up with a better reason for why are they repelling. They have to be, and they have the word virtual photon, so they already understand that it seems to move at the speed of light, whatever it is. It has all the aspects, has lots of features of just being this stuff moving the speed of light, this momentum. And the trick is how do you explain the negative momentum, the fact that the electron moves towards instead of away? And I'll give the simple answer is you have to understand that there has to be two forces. Just like there's two kinds of matter, there has to be two kinds of force.
If there's a suitable amount of neutrons in the mix. But to get the
So a suitable amount means usually an equal amount. So I don't know why she didn't just say an equal amount of neutrons. That's usually the suitable amount.
Protons close enough together.
Okay, with the bigger atoms, the neutrons become, you don't need to have extra neutrons. So I guess that she was saying it more accurately. So never mind.
Need very high temperatures. We're talking about
all right, so high temperatures, when we're really, this is another place where you get, the truth is temperature and pressure end up being the same thing. If you're going to cause stuff to move or vibrate, there has to be something that's causing the vibration. So there has to be something in the mix that's doing the causing, and that means there's force. There's got to be something in between the objects to cause them to be banging around, to be vibrating very fast, to be moving a lot. And so physics knows this. I mean, she knows that pressure and temperature are proportional. They're very similar. And one always seems to cause the other. You usually can't have one without the other. You can't contain a temperature without pressure, and you're not going to create higher pressure without increasing temperature.
Hundreds of millions of degrees. Such high temperatures.
So such huge pressures.
Indeed, much higher temperatures existed in the early universe briefly after.
So says her, like I said, they just made that part up because they have a creation story. And so somewhere in there, the Holy Ghost sprinkled, temperature on the universe. And then it went through a huge, giant expansion, which you could consider a giant cool down. The universe was this big. I can't even make the expansion. It's so huge, right? I mean, the universe went from being this big to being, as big as the United States. It just poofed. That's what their theory says, because that's the only way they can construct this story out of the little tiny pieces of evidence they have. But they have such little evidence that there's no hope here. They don't have any real evidence. They just have I don't even know how to describe it. It's like they got a carpet with 4,000 million, like people have lived in the room for 60 years and the rug was never vacuumed. So they have all this little stuff and they're just saying, oh, I'm just going to pull one hair out and say, that's the one. That's the guy. That's the one the murderer left behind. Could be any one of the millions of others.
The Big Bang. However, at that time, the density of matter was very high everywhere in the universe. It was a mostly structural soup of subatomic particles called a plasma.
See, they can't know any of this. I don't know. It's just... You would think, I've given evidence why you should doubt physics, okay? I mean, the 1/2 mv squared to describe energy, which is just silly. The two-slit, debunking all of the woo about that. And then gravity, giving you a simple explanation for why some energy is used up by material objects. But even without all that, I mean, can't you see that this story is not connected to a whole pile of evidence, that they don't really have any good reason to believe this story? There's no really good reason. They've just all decided we want a story, so this is the one we're going to tell, even though we really don't have any evidence.
Were no nuclei in the soup, just a mix of the constituents of nuclei. It was only when this plasma expanded and cooled that some of those particles,
by a magical process of magical expansion, blah, 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 blah,
managed to stick together. This created the first atomic nuclei, which could then catch electrons to make atoms.
So, I'm just arguing. The whole Big Bang theory is dependent on a tiny bit of evidence. Redshift, primarily, redshift could be explained as tired light in the sense that light traveling billions of miles hits lots of atoms. The atoms degrade the frequency of the light a little bit through each process, and over billions of years of travel, the frequency is degraded. Simple explanation, then you don't have a Big Bang anymore, and then you might start thinking that the universe just oscillates, between two states, a state of where the forces on the outside, creating gravity, are the forces on the inside of the matter, creating room for expansion. And that it just goes through those two processes.
For this, you get hydrogen and helium and a few other chemical elements with their isotopes up to atomic number 4. The process of making atomic nuclei, by the way, is called nucleosynthesis. And
yeah, we gave it a name, whoop-de-doo. I call it whoop-de-doo.
This part of nucleosynthesis that happened a few minutes after the Big Bang.
Yeah, it's a few minutes. I mean, you really think they could, a few minutes after the Big Bang. I mean, it's... they really just have nothing to base this on. Nothing.
It's called Big Bang nucleosynthesis. But the expansion of plasma after the Big Bang happened so rapidly that only the lightest atomic nuclei could form in that process.
And why would it? And what is the cause of gravity again? And the bent space already existed before the Big Bang. I mean, the whole thing has there's nothing mechanical in their physics. It's all magic forces.
Making the heavier ones takes more patience. Indeed, it takes a few 100 million years.
Says you again. So it's 4 minutes, then you're doing this, you're making pancakes, then, at 40 days, you've learned how to cook something more complicated, some kind of souffle. I mean, just...
During that time, the universe continued to expand, but the light nuclei collected under the pull of gravity and formed the first stars.
Yeah, right. So the stars are forming as it's expanding, which is a contradiction. Things are moving further apart, and yet they're moving closer together. Okay, sure they are.
In these stars, the gravitational pressure increased the temperature again. Eventually, the temperature became large.
So the gravitational pressure is the only words in here that really made any sense. But, now she's not saying temperature, gravitational pressure, see? So now she's on the right concept anyway.
Enough to push the small atomic nuclei into each other and fuse them to larger ones.
Right. So this is where the temperature and pressure thing is. So you can sort of understand that, there's some mechanism that, where you can bang things into each other with enough velocity, okay, to overcome a superficial rejection. So where the two ends are, obviously a blue endy thing isn't going to be likely to get in there. But if it's moving fast enough, right, then it can negate the collective force because it's moving fast enough to minimize how much force it's going to interact with. And by doing that, it can smash in there and, and have a place. But if it's not moving fast enough, it can't. And the only way it can move fast enough, that is enough of it moving, rapidly in succession even. Or you could argue that a pattern of bullets has a different effect than just shooting a single bullet. I can't tip something over. I can't knock something over with single bullets at a time. But if I shoot a series of bullets, then I can knock something over. So those principles are what's really involved. There's a mechanical principle. Now, she won't talk about any mechanical principle. She just have an animation that just pressure means push things in. But there won't be any mechanism. So the only thing I thought, that was sort of important to get out of this, in terms of, now she's on the subject of pressure and the protons and let's go a little further maybe.
This nuclear fusion creates energy and is the reason why stars are hot and shine.
So again, it creates energy just means it loses energy. You take two things that are a certain size, this size and this size. And when I smash them together, the new thing they'll become won't be quite as big, right, as the two. And so there'll be leftovers. And the leftovers are what flies off, and we call that energy. So the energy is just releasing, something that was trapped, and it's now not trapped. So it was in a structure, and now because you've rearranged the structure, there's extra stuff that was maintaining the structure. So again, because they don't have any word for this, they just say the word energy. But the energy wasn't made out of nothing. It was made out of something the thing already had. Both of the things. And you released the energy they had. And so these descriptions are just so weak. And, they're so... part of it, they already know that. I mean, I'm not telling her something she doesn't know. But you can't get the energy from no place. They know that.
Nuclear fusion in stars can go on up to atomic number 26, which is iron, but then it stops.
Iron.
That's because iron is the most stable.
Iron. Yeah, close enough.
The chemical elements. Its binding energy is the largest. So if you join small nuclei, you get energy out in the process until you hit iron, after which pushing more into the nucleus begins to take up energy. So
it takes more energy than you get back as pieces left over kind of argument. So you can't gain energy by shoving the nucleuses together because you won't have leftovers. Could say that kind of thing. You won't have enough leftovers to give you more than what it took you to push them together. So you have the energy it takes, the speed you have to hit them into each other, or the amount you have to hit into each other, requires more energy, more pressure. Requires more pressure essentially. So you have to compress a space more, and the amount of compression will take more energy than you'll get back out as pieces released. Some of you knew that's what she was saying. I was just making it clear.
So with the nuclear fusion inside of stars, we now have elements up to iron. But where do the elements heavier than iron come from? They come from a process called neutron capture. Some fusion processes create free neutrons, and the neutrons, since they have no electric charge, have a...
Okay, so they have no electric charge, they say. But obviously, you could kind of deduce that they must. Because they really are the thing that holds the protons together. Without the neutrons, the protons aren't going to be in a tiny nucleus. And again, they have no explanation for that. Beyond the fact that they do now know that... Well, she's going to say it, so I'll let her say it.
Much easier time entering an atomic nucleus than protons. And once they are in the nucleus, they can decay into a proton, an electron, and an electron.
Right, so this little electron blue thing, this neutrino-y crappy thing they put on here is just an invention. It doesn't make one of those. It just decays into a proton and an electron. That's what it's really made out of, and there is no other whatever this thing is. Anti-neutrino thing.
Anti-neutrino.
An anti-neutrino. I mean, it's just silly talk. Okay, that's not what takes place. So anyway, so they know it's a composite object and the neutron, and that's what makes she just has the proton sitting here while she has the neutron formula here, which is kind of funny. So why don't I put the electron in here in the picture, So people would really understand that's really what a neutron is. It's an electron and a proton. And somehow, okay, that works. And I would just say you can sort of deduce, okay. And this is what they're just not showing you. They're not giving you any deduction. They're not showing you how we came to these conclusions. So some of their conclusions I might agree with, but I mean, they never do show you. And it takes an awful lot of work to find out what experiments and what collider gave them some conclusion. Why did they draw this conclusion? Where do they test where neutrons decay? How do they test it? You know, you can't trust that they did any of those experiments in any kind of disciplined way, just as you can't trust them because of the two-slit experiment, for example, where they say things about it that are completely incorrect, that have nothing to do with the actual experiment and what actually takes place. So their reliability is way down. So you can't just trust them. All right, so this is the basic principle. They know that protons and electrons are opposite each other, okay? And they're opposite each other in exactly the same amount of oppositeness, okay? That is, if you were to reduce them to a point, their charge is exactly inverse, okay? So whatever the negative thing has, the positive thing has just as much of it, all right? It produces just as much at a distance. They both have the same, there's going to be the same amount of measurable stuff coming off of them, so they're equal. Now that could make you say, well, they're probably got to be equal in a lot of ways. Now they know the masses are different, they say, but they don't measure mass by sticking a thermometer in, or they don't measure mass by asking it how much do you weigh. They have to drag it out of its circumstance and do something else to see how much it moves and all this kind of stuff. It's not that simple, measuring these things masses. You can't put it on a scale because the scale is going to be made out of electrons, right? I can't measure an electron by putting it on a scale. That ain't going to work. And when you find out that when they do measure, they're using this formula when they do measure, okay? They're using the silly formula, 1/2 mv squared. The formula just is absolute nonsense. Never should have been accepted by physics as a real physics formula. The absolute nonsense energy formula. And they're using that in the process of determining how much the electrons weigh. So how accurate do you think it really is? They say, oh, we've got it down to 25 decimal places now. So what? Because your formula is wrong, so you really don't have the right answer. So anyway, that's just, it's all important stuff. I got to do that blue. Anyway, so what you could figure out, right, if this is a neutron, this collective thing, I can afford a little tiny bit more chalk. Now, you could sort of understand that you might think it's neutral because it has equal parts. And if those two equal parts were just spinning or something, you could say, oh, yeah, it's, it flashes pink, it flashes blue, it flashes pink, it flashes blue. Oh, it ends up looking purple. It ends up looking neutral, but it's not really neutral. All right, that would be the first thing I would tell you to kind of understand. So what you're really doing is adding another proton, okay, to this mix, and you're creating a pattern now. Now you have a pattern, and if these are opposite forces, that is, the pink things are attracted to the blue thing, so they want to go towards the blue, right? They want to go towards the blue really strong, but they hate the pink just as much. So that these these arrows would be commensurate in terms of the force, that they're applying. Okay, the attractive force this way versus the repulsive force that way. And you can figure out, that, okay, well, if I did put an electron between two protons, what would happen? Even without me telling you there's a mechanism, you could really understand it. But even without me giving you the answer, the full answer, the more complete answer, you could already say, yeah, okay, I get that. I could arrange these things. I could put another pink one here, And if I did this in three-dimensional space, I could have another pink one here. I could get these pink things relatively close to each other just by always keeping a blue thing in between, and that way it'll allow them to get much closer to each other than they could get. So where they have to stay, this one is probably going to have to be a much further away, like here, to be accurate. But anyway, so you can understand the repulsive could be here, all right, and there could be attraction here. Whether I put a proton in the middle or an electron doesn't really matter. You get the idea, because the charges are the same. Now, the reason why the protons are in the nucleus is probably because the protons are heavier. They have the same charge, but they are in fact heavier. They're harder to move. So they get stuck in the center with some electrons as being part of the neutrons, and that's why you can make a nucleus, because there's something to mitigate against the charges. Now, I'd say the yes, down there. I would argue that you can understand it more simply, the mechanism, by understanding that there's really two forces. That there's really two universes. The universe of the electron and the universe of the proton. And the simple rule is when a proton force hits a proton, it causes momentum. That means it causes the proton to move to a new location until it's hit by an opposite force, and then it reflects. And it reflects. So basically the rule is the two things have opposite behaviors when they're affected. So when you mix the two universes, the only trick is that when a pink force hits the blue thing, it doesn't move the blue thing, it just diverts the force. So the proton force just gets diverted by an electron, and protons are doing the same thing to the electron force. So every time when a blue thing hits a proton, it just gets diverted, and they are moved by, this one will be moved by the blue force, and this one will be moved by the pink force, the red force. And with that simple understanding, you can understand why the two reds move each other. So that means if the force gets trapped between them, it'll bounce back and forth, and the closer I bring them together, the faster, the more often. Sorry, you got to be careful about language. It doesn't move any faster. It just obviously hits more times, okay, because it's trapped between the two. So you're going to understand if there's more pressure, that is, there's more external pressure between, in an environment, that's going to mean that all the pieces are going to be pushed closer together, which means all the pieces that don't like each other are going to reflect a lot more reflections, and they're going to push against the pressure. So the more pressure you apply, the more pressure the little bits push back with. And so there's an equilibrium there that always matches. More pressure will create more pressure. Will create more pressure. Will create more pressure. All right. So the idea is that these atoms are being made inside of suns. Well, maybe I'll let that dry. Take a little break, and I'll be back momentarily. Alright, should be back and such. So let's go to understanding where the pressure comes from and all that, where they don't really explain any of that stuff. So if you're just one little piece of stuff in the universe, right, there's only so many things that can hit you, right, because you're only one little tiny piece of something. So there's only so many pathways that get to you, right? So there's only so much jiggling that can happen to you. So there's a certain amount of pressure you could say the universe would have. And so we could say, I could just make I'll just make a number up. Let's just say 10 things hit per second. So a thing could hit from this direction, or a thing could hit from this direction per second. Now the real universe, it's probably a billion, but let's just say 10. You can sort of understand only 10 can access this one little point. Now, the trick is if I become bigger, as I gain mass, then all of a sudden the places from which I can get hit are now increased with the fact that I've got more mass. Obviously, you could see that, maybe if I draw it as a square, it'll be more obvious, but you can see that my surface is now larger. So there's more, this one can hit me, this one can hit me, this one could hit me, this one could hit me, all kinds of angles, but I've increased the surface area that can be hit in the direction of this center. That is, the energy has a component, okay, that has a, this one has an obviously large component in this direction, right? If I made a triangle here, you can see it's a large component in this direction, a small component in this direction. I can have all kinds of angles. Like this angle would have a very small component in that direction and a very large component in this direction, but it's not hitting the surface in that direction. But the point is what you might be able to understand is that as I increase the size of the object, the pressure on this thing is now getting bigger and bigger and bigger and bigger, because all of the pressure hitting here, no matter what angle it hits at, no matter how it hits, whether it's on the center or off the center, it doesn't matter. The Earth is going to, the structure is going to convert it into energy in this direction. That's going to be the direction. It's going to convert the component in that direction. So it's going to take whatever component is in that direction and go in that direction. So now you can understand that the pressure before was only 10 things hitting me, right, per second. When I'm this big, it's 10 million things hitting me per second. I've so increased my surface area, that is the area that can be possibly hit, is so much larger, and all of that energy is going to tend to move towards this little guy who started off right there in the middle. And so now he's going to have 1 million pounds per square inch instead of 10 pounds per square inch, or whatever you want to measure the pressure by. So the bigger the thing gets, and the more, obviously density matters, but I don't want to get into a density argument. We'll just say it's all made out of the same substance and has the same. But obviously the heavy things are going to sink into the middle, and the light things are going to go to the surface. So obviously there's going to be a mixed density in this object. But it's really not important to understanding that even if something hits at this stupid angle like this, there's a tiny component of it that is actually going in that direction, and that energy will be realized in that direction. And so all of the energy is getting collected from all of these impact points, all these places the Earth gets hit, and all of that pressure eventually goes right down there. So that's how you build up the pressure on the inside, is you're constantly moving pieces of matter in those directions. Little electrons and protons are constantly moving in that direction. By the way, creating gravity, because you're moving matter. Okay, and when you move an electron, the force gets slowed down. So the simple principle would be, if you hit an electron with a piece of force, it sticks to it, moves the bit until it gets somewhere else. Well, that means the force, instead of going the speed of light to get to here, it's got slowed down because it had to move the matter. It moves the matter slower than the speed of light. Therefore, a force bit that should have been here is only going to get to here. And if you calculate that distance and do a velocity equation, you'll find, oh, its velocity slowed down. So when light goes through glass, it loses 40%, technically, in a way. A way of describing it would be, it lost 40% of its velocity. And if it lost 40% of its velocity, then you could argue it lost 40% of its momentum for that period of time. Now, once it leaves the glass, it's back to normal. It's going the regular speed because it's not pushing electrons anymore. It's not getting slowed down anymore. So it goes back to its normal cruising speed. But the fact is, the universe lost some energy because this is here when it's supposed to be here. And that's just a fact that it covered less distance, which means it didn't move the speed of light, technically, and therefore it didn't have the same momentum for that period of time in the universe. And so when you calculate all the momentums through all the time, so you just count all the seconds, how much momentum is in the universe, well, every time matter's moving, there's a little less momentum in the universe. And that ends up being gravity. All right, so I didn't mean to do gravity because we're just doing atoms, but you see how that's all. When you have the right answer, it all connects. Okay. So anyway, so we're just doing the pressure argument, and I think I've made the point that the bigger I make the object, I end up converting that entire surface area into this little center's surface. and all the pressure hitting that big giant surface will now be felt by this little one. So I'm collecting billions and trillions of times more energy than this thing could by itself collect. So being part of a group means this little atom in the very center is going to be under a hell of a lot of pressure. I mean, all of the weight of the Earth is going to be stacked on its head. So much pressure. And in those environments is where you can rearrange electrons and protons. You can imagine if you have a bunch of pressure between the electrons and protons, that is, there's energy trapped between them, bouncing back and forth, you can understand that if you create a higher pressure on the outside, there's a point where they equalize in a way, and you could just move things around without causing too much trouble, because you've equalized the pressure. You have much as pressure on the outside as you have on the inside. And technically you do that in free space. I mean, everything just gets bigger to accommodate the fact that you've moved it from a different environment to a new pressure. But I'm just saying that there's an obvious, it's not obvious, and I shouldn't say obvious. It's obvious that everything's going to be, in high pressure, everything's going to be very close together. So that's a way of thinking about it, right? In low pressure, the atom is it's all equalized, right? Say the atom's this big, right, in low pressure, and then the atom's only this big in high pressure. Same equalization, same thermal equilibrium. The pressure on the inside is the same as the pressure on the outside, and everything stops moving in one of those directions, out or in. But what you could really understand about it is that under high pressure, these bits are really close to each other, where in low pressure they're far apart from each other. So it's a lot harder to move this far enough to say, I'm going to exchange this bit for this bit over here, knock this bit out, or whatever you're going to be doing. Whatever movement you have to do the movements over a much longer distance to rearrange the parts, where under high pressure the parts are much closer together, and so it's easier to rearrange them. Yeah, that would be a good way to understand it. I think an adequate way. It will suffice, says I.
If they do that, they have created a heavier element. A lot of the so-created nuclei will be unstable isotopes, but they will spit out bits and pieces until they hit on a stable configuration.
Yeah, that's also a little bit tricky rhetoric. They'll spit out bits and pieces. Well, radioactive decay really isn't just spitting out bits and pieces. It's really about the fact that the nucleus is unstable and it breaks into pieces, and then it releases a whole bunch of them at once. It's not that a radioactive element is spewing out little pieces all the time. Each atom is spewing out pieces, slowly spewing out extra pieces. No, it's that the instability just means that it gets to a point where the atom itself can be easily broken into two, bisecting the nucleus. And when you separate the two nuclei, just like where it took extra energy to push them together, well, when you make the big atoms, it gives you back extra energy when you break them apart. You end up with pieces left over. And it's the leftover pieces that are the decay moment. It doesn't release an electron at a time. One atom releases, 4, plus all the energy associated with the electron.
Neutron capture can happen in stars just by chance every now and then. Over the course of time, therefore, old stars breed a few of the elements heavier than iron, but the stars eventually run out of nuclear fuel and die.
So again, all this sounds blah, 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 blah. Nuclear fuel just means that they end up with heavier elements, and the heavier elements start clogging probably the mechanism on that inside. It's probably like glue to this engine that's converting hydrogen into helium. And it stops converting hydrogen into helium because it has too much of these waste products it's created. These heavier elements keep trying to get into the furnace. And it's like water. The furnace is cooking. It's really going well, but it's producing water as a byproduct. You could sort of understand the water is swirling around. I'm just saying water just as an opposite to fire. and then the water falls back into the furnace. It's like the smoke from the smokestack goes up into the atmosphere, goes around the planet, let's say, and then it condenses and falls on your fire as rain. That kind of. So that's why the suns stop, producing, is because they get too dirty. They get too full of all these little heavy elements they made, and they can't fuse those anymore. They can't do anything with them. They can't break them. They can't build them into something else. So they just end up clogging the pipes. I think that's a better explanation, frankly.
Of them collapse and subsequently explode. These supernovae.
So the explosion part is because obviously when all this is happening, you're containing more and more pressure. So the heavier, as you start making heavier elements, you start increasing the density of the sun. And as you increase its density, that's the same thing as saying increasing its size. Density means it can capture and move energy more effectively. So the heavier it gets, the more effectively it's moving pressure. So the internal pressure gets higher and higher as the elements inside the sun get heavier and heavier.
They distribute the nuclei inside galaxies or even blow them out of galaxies. Some of the
So that's all kind of big talk, this whole cosmology thing. We know the supernovas don't happen very often, blah, 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 blah. But anyway, the theory, okay, that the whole thing ends up getting dirty and the pressure builds up and it blows up is like a same kind of theory you could use at a refinery or something. As you're refining products, and you can end up having a bunch of sludge or some other thing clog your pipes, and then the pressure builds up and the thing blows up. Not miraculous, not required any of this mush. It's not necessary. Alright, should be back in such. Continuing.
Lighter elements which are around today are actually created from splitting up these heavier elements by cosmic rays. However, neutron capture in old stars is slow, and stars only live for so long. This process just does not produce sufficient amounts of the heavy elements that we have here on Earth. Doing that requires a process that's called rapid neutron capture. For this, one needs an extreme environment of very high pressure with lots of neutrons that bombard the small atomic nuclei.
Right, so this is all some sort of specialized kind of, this is what their math says, or this says, or that says, but there's no real evidence explaining why I should believe in any of this stuff. It's like even the existence of a neutron star. I mean, it sounds interesting, but what would be the process? You could argue that if you made atoms really, really cold, that is, suns that were not on fire, that you might have some hope. But just the whole idea of gravity sort of teaches you is that the more gravity you have, the hotter the center is going to be, the higher the pressure. And, how do you get say a neutron star would just be basically saying, okay, you have a bunch of electrons and protons perfectly stacked. So you've maximized their distance from each other, minimized all the noise. So it's almost like you need a cold thing to do that. But whatever. I'm just saying that they don't have any real mechanics. They can't show you mechanics of any of this taking place. They can just say it exists. Not because they've seen any of it. I mean, we can't see these tiny little points in space, so we can't tell how big, when they say something's making gravity, they can't tell whether it's, it could be 10 solar systems across, it could be 100 solar systems across. They can't tell the difference.
Again, some of the neutrons enter the nucleus and then decay, leaving behind a proton, which creates heavier elements. For a long time, astrophysicists thought that rapid neutron capture happens in supernovae, but that turned out to not work very well. Their calculations indicated that supernovae would not produce a sufficient amount of neutrons quickly enough. The idea also...
to produce neutrons, you have to get them from somewhere again, so the argument is back. And also, you have to understand that the neutron and the hydrogen atom are basically made of the same things. So if... certainly it's not something you're going to have happening inside of an active sun, because an active sun is using the hydrogen to make helium, and it's not going to waste it to make neutrons.
Did not fit well with observations. For example, if the heavy elements that astrophysicists observed in some small galaxies called dwarf galaxies, had been produced by supernovae, that would have required so many supernovae that these small galaxies had been blown apart, and we wouldn't observe them in the...
Well, that's a little bit reachy, frankly. Frankly, there would be a supernova every day or every minute or every 3 hours or something. You wouldn't need one every millisecond. I mean, it would take one every like 15 seconds to really disrupt the galaxy, I think. So I think that's stretching it a bit.
First place. Astrophysicists therefore now think that the heavy elements are most likely produced not in supernovae, but in neutron star mergers. Neutron star...
So this is more just made up stuff. So this is just guesswork made out of tiny, like I said, they're not just shreds of evidence. They're not even close to a good piece of solid evidence. And I don't know how to, it's I don't know. I don't even know what to describe it to, because we don't really, there's no example of this Clouseauian kind of evidence detection, where you can just, you find a fish that, ate a ring 15 years ago and the ring's still stuck inside the fish or something. You have an extra, I mean, it's just some sort of bizarre reasoning that they're using to draw this conclusion about what took place. But they don't have any hard evidence.
Are one of the remnants of supernovae. As the name says, they contain lots of neutrons. They do not actually contain nuclei, they are just one big blob of super dense nuclear plasma. But if they collide, the collision will spit out lots of nuclei and create conditions that are right for...
So, says them, right? So again, just more says them, blah, blah, blah. And these mergers happen where and how. So there should be a whole bunch of suns then on the edge of a galaxy that get hit by all these neutrons. And all of those suns change their character. And then they start supernovaing more often because they got full of neutrons. They got fed a whole bunch of neutrons. So even this doesn't make any sense, right? You can imagine if this only happens like in these certain locations in space, that whatever this is doing isn't going to hit every bit of the galaxy evenly with its little speckle of neutrons. No, it's going to hit one side a lot more than the other side. And we'd see those kind of differences. We'd see galaxies that have supernova much more often on one side than the other side or some kind of thing like that. So, all this can be counter-argued, but it has to be counter-argued based on the observations from which they took a tiny piece of evidence, made a gigantic leap to a conclusion. And none of that is in any of these videos. Where do you compile the evidence for these conclusions?
Neutron capture. This can create all of the heavy elements that we find on Earth. A recent analysis of light emitted during a neutron star merger supports this hypothesis because...
Yeah, so again, the very existence of this merger was never seen. This isn't with some kind of LIGO bullshit. And they saw a supernova, okay, that came from the same direction as the LIGO thingy, okay, and they're saying it's a merger of two neutron stars. Inside a galaxy, I suppose. I don't know. But, oh, please. No, thank you.
The light contains evidence for the presence of some of these heavy elements. You may have noticed that we haven't checked off the heaviest elements in the periodic table, and that there are a few missing in between. That's because they are unstable. They decay into smaller nuclei in times between a few thousand years and some microseconds. Those that were...
Well, if it was a few thousand years, then we should be able to put some in a bottle and say, there it is. Yes, but finding some arrangements, it's just an arrangement, right? The 100 or so elements in the periodic table are just telling you, I'm going to give you polygons, and I'm just going to say, here's polygon, polygon, polygon. You can arrange them in certain ways where they're symmetrical, in 3 dimensionals. And there's only a certain number of arrangements that actually are going to work. And then when you try to go one more level out, it just isn't going to work anymore. So you can't make any more. So it's just basically saying, look, we've got 4 layers of physics here. There's 4 layers where we can put these polygons. And as soon as we go past those 4 layers, it gets less and less likely the thing's going to hold together.
Produced in stars are long gone.
6 layers.
We only know their properties because they've been created in laboratories by shooting smaller nuclei at each other with high energy. Are there any other stable nuclei?
High pressure again, but anyway. Energy, pressure, same thing.
That we haven't yet discovered? Maybe. It's a long-standing hypothesis in nuclear physics that there are heavy nuclei with specific numbers of neutrons and protons that should have lifetimes up to some 100,000 years. It's just that we have not been able to create them so far.
So, so they're arguing they can pile on, but I would argue that the piloning process depends on the original charge of the protons, and you need to have a nucleus that's heavy, very heavy, to sustain electrons, way far away. And that's where the whole thing starts to, you just went past the limits of what you can actually make that'll stay in one piece. But whatever. Let them go ahead and try.
Nuclear physicists call it the island of stability because it looks like an island if you put each nucleus on a graph where one axis is the number of protons and the other axis is the number of neutrons. Just exactly where the island of stability is, though, is not clear, and predictions have moved.
I don't know. I think it's pretty clear, but whatever. It seems like the geometry just is you add another proton, add another proton, add another. That seems like the theory. So it's not that complicated, and all of a sudden it starts to get really difficult to add more protons. So
moved around somewhat over the course of time. Currently, nuclear physicists believe reaching the island of stability would require pushing more neutrons inside the heaviest nuclei they previously produced. But the maybe most astonishing thing about atoms is how so much complexity, look around you, is built up for merely 3.
Yeah, well, that's chemistry, actually, but whatever. 3, she's going to say, so let's see what she says.
Ingredients. Neutrons.
Right, well, there's 3 ingredients with 100 configurations. So it's the 100 elements that make for all the complex chemistry. I mean, you do have to include that middle part.
Protons and electrons.
It'd be fine if that's what you believe. So this is where it's just gobbledygook, right? Because that's not what you believe. You believe there's antiparticles for every electron, and there's antiprotons, and there's positrons, and you believe in 400 or so wacky little silly things that are somehow bouncing around inside of this atom. So why this is where it's so incredible. She just makes this point that isn't it just amazing that the universe is just made out of electrons, protons, and neutrons. And that has nothing to do with the Standard Model at all. The Standard Model says, no, it's quarks, and it's tau muons, and it's neutrino tau fluons, and all of that crap. So she's just denying the physics and just lying, to pretending, because that's not your physics, that's not your math, that's not your whole game you're playing. It's all this other crap you've invented. I mean, it's disgusting. I mean, it's just so duplicitous to sit there and tell me, oh yeah, it's just made out of this simple stuff. Well, that's not what you believe. It's not what you're selling.
I hope you enjoyed this video.
No, why would I enjoy duplicity? That's a horrible thing to enjoy. So yeah, yuck, I hated it. Yeah, so there, that's what I did. She's, she didn't have a sponsor this week, I guess, so she's selling her Patreon.
You can now support this channel on Patreon.
Yeah,
so
Patreon.
If you want to...
Okay, so it's Irene and Patreon. Yeah, you can
be
pat
part
her.
of the story. Go check this out. I want to...
Yeah, I guess I'll make Pincheon, and then you can pinch her.
Especially thank my super supporters on Patreon.
Oh, these people, come on, grow a brain, support real physics, don't support this mush. Prodan, I don't think that's his real name. Jeremy Payne, Jason Partry, Ben McCarty, Archibald, is that what that is? Archie. Brigington. Yeah, well, you're on the wrong team, fellas.
Your help is greatly appreciated. Thanks for watching.
So she could be duplicitous. You just saw her be duplicitous, didn't you? All you little supporters of bullshit. Didn't you just see huge duplicity? She knows the Standard Model is made out of all kinds of crazy, crappy little particles. 400 of them. And she just said, oh, isn't it amazing that the universe is just made out of electrons, protons, and neutrons? And again, the real argument would be neutrons are electrons and protons. So yeah, the universe is just made out of electrons and protons. Two kinds of matter, plus and minus. And if you just have two kinds of force on one side and two kinds of interaction on the other side, guess what? You have the whole answer. The universe is 6. Yeah, 2 plus 2 plus 2. 6 dimensions. Up, down, 6. It works, it all connects. It's all about 6s. Well, we have 2 testicles, 2 eyes. Yeah, I'll just add them up, right? 2 ears, 2 eyes, 2 testicles. There, 6 again. We win. Never, just having fun. Well, my kind of fun. Might not be fun for you, but, it's fun for me. So anyway, that is enough of a video. So we'll do the... fuck you idiots. Yeah, fuck you people. You're all just so goddamn gullible, dupable, stupid. Ugh, it's just terrible. It's just horrible to watch. It's like if your brain dysfunction actually had a physical representation. You get what I'm saying? I mean, you're like all a bunch of deformed little kids. All horrible deformities because your brains are all full of crap. And you understand why, looking at that makes me queasy. Ugh, very uncomfortable. It's very hard to look at your people, your brains, because they're so frickin' deformed and ugly. Ugh, it's horrible. Anyway, that's probably enough. Yeah, that did it. Well, finished you off. Okay, never mind. Sun's out. It's very bright in here. Anyway, till the next time and such, so forth and what not. This has been a DraftScience video presentation. Such.